Exponential functions. The goal of this lesson is to give a meaning to irrational exponents as limits. We are going to go over what exponents we have all actually seen during the K-12 education, but irrational exponents were not given a real meaning. And then we're going to define a number we are going to call by a letter, E, which will be the natural the base for natural exponential and natural logarithmic functions, and then find the derivative of exponential functions. And then this requires as prerequisites the concept of derivative and rate of change, the concept of continuity, and also how one evaluates rational exponents. The motivation for this is that there should be a meaningful understanding of how we build an exponential function, because in real life, exponential functions play a big role in modeling many physical and non-physical situations. And so we want to understand the behavior of the exponential functions and the role in the applications. So let's take a look at what exponential functions are. First of all, the form algebraically is a base with an exponent where the base is constant, a number b that has to be positive and different from 1. And we can quickly convince ourselves that those restrictions are really necessary. The first one is just to avoid, for example, if we had a negative base such as -1, and then you put an exponent 1/2, we would be attempting to find the square root of -1, which is not a real number, right?
Right.
But that cannot happen if the number we are taking a power of is positive. Then all powers are defined, which justifies why the base should be positive. Why don't we want it to be 1? What's the problem with a function that looks like 1 to the x? There is no problem, but what is 1 to the x equal to?
1.
1, no matter what
straight.
x is, right? So this is not an exponential function, it's just a constant function at 1. And so to avoid that, we'll say the base is not 1. That's all there is. So during the years of schooling, one gets acquainted with how to evaluate some of those exponents as, we don't even call them back then an exponential function, but for what kind of exponents you have a simple way to compute b to the x. If x is 2, for example, right? What would you do? What is b to the power 2?
It would be b times b.
Exactly,
B2
perfect. b times b. And in general, if we have a natural number, which means a positive integer, the idea is the same. You take n factors all equal to b, you multiply them together, and now we have a meaning that most people have seen in their middle school years. And then eventually it gets extended to their opposites. So if the exponent is now a negative integer, so here it says n positive integer because I have a minus n, then it's a negative integer. Then we define the corresponding value of b to the minus n as a reciprocal of b to the n.
Right.
And then again, another extension that many people have probably seen during their algebra in high school is what happens if the exponent x is a rational. Rational means a ratio of two integers. So it can be written as p over q, and we'll just focus on positive integers, because if 1 is negative, then the quotient is negative, and we'll just do the reciprocal business that we know from this line. And so for a rational exponent p over q, there's the bar missing here, all that we do is the power is the numerator, and then there's a qth root where the denominator indicates the index of the root. And in principle, one could evaluate this by hand. If there is an algorithm to take roots, which there is, powers, of course, can be just multiplied out by hand. Not that we want to do it by hand, but historically that's the way things were done. The question is what happens when that exponent is an irrational number, okay? And so now we have powerful tools and concepts, the idea of a limit. An irrational number, you could, for example, think of the square root of 2, which is 1.41421, but that's not all. It goes on forever. Irrational numbers, remember, in their decimal expansions are not repeating and never ending. So however many digits we write, it won't be exact. So that's the meaning of the dot, dot, dot. It goes on forever. But then we could say that if we start adding one digit after another, after another, after another, in the limit, when you have the infinitely many digits here, you would have exactly the square root of 2. So we are thinking of approximating an irrational number through rational approximations. And so how do we do that? Well, we use limits. So if x is an irrational number, how do we define b to the x? We take rational approximations. By approximations, we mean let's find a sequence of rational numbers that approaches that irrational number x. And then we can evaluate the powers with rational exponent, because we have a formula that works for all rational exponents. And if we then take the limit, that's what we want to use as the value of b to the x, which of course makes the exponential function continuous, because then we are saying the limit of the powers is the power of the limit, because the limit of the r's is x. Here we are assuming the limit of x as x approaches r is, sorry, it's backwards, as r approaches x. The exponent is called r, and so as r approaches x, of course its limit is x, which means in the exponent I have a limit, and I brought the limit down from the exponent. That means the function is continuous. But here we are using the switch of where we put the limit to actually define, give a meaning to something that until now, probably for most students, didn't have a meaning. Okay? So now we have an honest exponential function that is defined with an exponent being any real number. Rationals were already known, and now we fill in the gap with irrational exponents. So now we can actually start to study those exponential functions. Let's look at an example. Let's just use base for definiteness, base 3. And then let's think of what do we mean by 3 to the power square root of 2. Well, as we indicated a couple minutes ago, we are squeezing the value of this irrational number between rational numbers that are really close, smaller. That's the one we had seen you obtain by chopping the end of the infinitely many decimal digits that root of 2 has. And then this one is slightly bigger. Why is that? Well, because remember that the square root of 2 is approximately 1.41421, and you go on. So anytime you chop, let's say you keep just the 414, that's necessarily smaller because there's more stuff that we are not looking at, right? Mm-hmm. Yeah. But then if I add a 1 to this number 4, that's what the 415 is. Why can I say that's already bigger than the root of 2? Because I would have 1.415. You see that this number is bigger than this one because this one has a 5 in the place, this one has a 4, and all the digits before are equal. So anytime we do that, wherever we chop, if we chop after the 1, now we'll make that 1 a 2, and then we'll be able to say that 1.41422 is bigger than the root of 2. Yeah. And we'll have 2 columns here that will hopefully give us sequences of numbers whose limit we can see visually. But the important thing is that if we take those sequences, remember what we just said in the previous slide, that if you have an irrational exponent, you actually evaluate rational exponents that are converging to that irrational exponent. So we start with those two, one smaller, one bigger, and then what do we evaluate? Well, what is 3 to the power 1.414? How can we write 1.414 as a fraction? Denominator is 1,000, and the numerator is 1,414. So according to the formula for rational exponents, we have a root with the index of the denominator and an exponent the size of the numerator, right?
Yes.
And that will be exactly, this is not approximation, by definition, the value of 3 to the power 1.414, which hopefully will be an approximation to this number we don't know. And it will certainly be smaller because exponential functions are increasing. You take a bigger exponent, bigger value of the exponential. And so the number turns out to be the first 5 decimal digits, or rounded to the first 5 digits, 4.72770. And now we do the same thing coming from above with a 1.415. So it's the 1,000th root of 3 to the power 1,415, which rounded to 5 decimal digits is 4.73289. And you see that already those two numbers, even though they are not too close, they seem to indicate that possibly the 4.7 that they share might be actually the first 2 digits of this value we are trying to approximate. So how do we try to see if that is indeed the case? Well, let's take one more decimal digit. Instead of 1.414, let's go on to 1.414, and then comes a 2. Which is what this line does. So you have on the lower end 1.4142, which is smaller than the root of 2. And then on the higher end, we have the 1.4143 that is bigger than the root of 2. But now we can also take the roots and the powers. So for example, what is the actual value of this 3 to the power 1.4142? The answer is, well, this is 3 to the power 14,142 over 10,000, which by definition then is what? What power of 3?
The one that, or 14,142.
Excellent. And then a root with an index that was the denominator 10,000. And that yields, again, as a 5-digit approximation, 4.72873. If we do the same thing with a slightly bigger number than the square root of 2, that's the algebraic expression with roots and powers. 5-digit approximation is 4.72926. So that reinforces our guess from the previous line that the 4.7 seems to be really fixed now, because now it looks like the 4.72 maybe is fixed also. Those two numbers seem to be very close to each other. And so if we want to see, is this really working, let's do just one more line to convince ourselves, which means let's add one more digit to the decimal expansion of the root of 2, 1.41421. And then there's the rational expression with roots and powers. And in 5-digit approximation, we obtain 4.72879. And when we do it with an exponent slightly larger than the root of 2, that's the one I underlined, 1.41422, a little bigger than the root of 2. Here is how it is defined with roots and powers. And if we evaluate that, we obtain to 5 decimal digits 4.72884. And now we see that those two numbers, 4.72879 and 4.72884, are really close to each other. They share already the first 4 digits. But the fifth one, here one might intuit or guess that if you look at the sequence of these numbers, they are increasing, right? The 4.727 became 4.728, followed by a 7.3, and now followed by a 7.9. They seem to be increasing slowly. So possibly you might guess that the next digit after this 8 in this sequence might end up being what?
It would be 8.
It would possibly and probably be an 8. So maybe this is approaching 4.728, and who knows what, which seems to match what is happening with this sequence. 4.73289 here got smaller to 4.72 instead of 73. 926, and now 4.72884. So it's getting smaller, and therefore we can trust that those first 5 digits may be the ones. And it is indeed the case. If we were to do this, carrying it to the limit, which means the dot, dot, dot is go on forever, then we would have a limit of this sequence and the limit of this sequence matching each other. And if they match, that is the value we will assign to the square root of 3 to the power square root of 2. That indeed starts with those 5 digits and even followed by a 0. So you were really close. So this way we now have hopefully a thorough understanding of what the exponential function means in terms of its values. And let's now focus on finding the different types of behavior that exponential functions may have. So we know that the base is positive, we already said it. The function will be continuous for all real numbers x, always. It doesn't matter whether b is close to 0, or even if it is equal to 1, which we know is not exponential, or very large, the function will be continuous, because remember we filled in the gaps for irrational numbers using the concept of continuity. But there may be 2 very different types of behavior. So here you have 4 exponentials plotted that correspond to different bases. The blue one is the graph of y equal 2 to the x. And then the brown is y equal 3 to the x. And you see that those, even though they are different curves, they share what one would call the general behavior. They seem to be, as x goes to the left to minus infinity, they both seem to be going to 0, right? What can you say about their y-intercept? They share it. It is at y equal what?
1.
Excellent. And that's true for all exponentials, just because b to the power 0 is 1. And then they seem to be going to infinity as x increases. And we see, and it matches our intuition, that the larger the base, the faster it seems to be going to infinity. That's just a statement that powers of 3 are larger than powers of 2, right? Positive powers, not negative. So what is 2 squared, for example?
4.
And what is 3 squared?
9.
A lot bigger. So that's what this is representing. What happens with the green and the red curve? Well, they correspond to numbers that are between 0, and remember the base is always bigger than 0, but now they are less than 1. So the red curve corresponds to 1/3 to the power x, and the green one is 1/2 to the power x. And that is, again, a behavior that is shared by all exponentials with a base that is between 0 and 1 in this case, and in contrast with the bases that are bigger than 1. And what about the limiting case for the base when it is 1? Well, we already had said that is not an exponential function. It is the constant function where the value for any input x is always going to be 1, which you see matches really neatly what one might imagine is happening to these curves, the ones that are decreasing for numbers b that are between 0 and 1. We can imagine those will keep coming down like this, and they seem to be approaching this black line, which then matches our idea of continuity with respect to the base b. The base b, as I move down this fan, is approaching 0, and then we get, 1, not 0. And then we get 1 to the x, the corresponding limit, which is the constant function at value 1. And the same thing happens with the ones with positive base. As the base decreases, these are curved, not straight, But as the base decreases towards b equal 1, that is, we approach the black line. Okay? So it all feels fitting well together and matching our intuition. And remember, the base equal 1 is not an exponential. That's why we require that be different from 1 if you want to have an exponential. So what can we do as a summary? Well, what we just said can be summarized. We look at exponentials b to the x. We have two separate cases, the one where the bases are small, let's call them, between 0 and 1. And then we know the functions are decreasing, but they always have the same intercept at 1. And then their limit as x goes to infinity is always 0. They have this horizontal asymptote on the right. But on the left, they go to infinity. And the mirror image of that is what happens when the base is large. And large doesn't have to be very large. We mean just bigger than 1. Then the functions are now increasing. Same intercept at y equal 1 when x is 0. But now the limits are exactly opposite. Now when x goes to minus infinity, we are looking at the horizontal asymptote, value at 0. And then as x gets larger and larger without bounds, so does the exponential. Okay? So this is a quick summary. They all have domain from minus infinity to infinity, and the range positive numbers, so we can summarize that as 0 to infinity.
Okay.
All right, this is a quick recall of properties of exponent that you probably all have seen. Suppose that we have two numbers a and b that are positive, so we are thinking of those as possible bases. And then x and y, two real numbers, we are thinking of them as exponents. What can we say about adding the two numbers in the exponent? Well, that is the product of two exponentials consisting of the same base being multiplied together, right? You probably are more used to seeing this in the reverse order, that a to the x times a to the y, product of powers of the same base is the sum of the exponents, right?
Yeah.
But of course, equality is symmetric, so there's no reason why I should invert the order. We can take it in any order, that's the property. So read from right to left, it says that the product of two powers of the same base is the power with the added exponents. Okay. And what would be the next one, you think?
A to the x minus y.
Right. What happens if we subtract in the exponent? Then we get, instead of a product, a quotient of two powers of the same base. And then we have the one with power of a power that multiplies the exponents. Those are two exponents, power of a power, we multiply them. And then there is the one that is a distributive property of the exponent with respect to multiplication. And that says, that's why I also wanted another base b, that if we have a power of a product, it is the product of the powers, in short. Okay? So this is a quick review. The thing is that it now holds for all real exponents with the limits the way we define them. Okay. Now, one property that may not have been stressed enough during the high school years when one first looks at exponentials is what is arguably the most important property of exponential functions. So let's take now the exponential a to the x and think of what happens if you shift x by some fixed constant. So k, let's pick a number k. It could be 2, but it's not a variable. Here the variable is x. And so I'm thinking of adding k to the input, and the result is that an exponential function is multiplicative, we'll give a definite meaning to that in a second, over any interval of length k, where k is any number. And so what do we mean by that? Well, we mean that if you put a factor a to the k, then the shift in the input results in multiplying. So if you are thinking of f of y, that's a to the power y. That is what we have on the right. But now I shift the input by k, then that value f of y gets multiplied by a constant number. Y continues to be a variable here, okay?
Okay.
But then there's a constant factor. So in that sense, an exponential is multiplicative. You fix an increase to your input, whatever the input was, and then the output that corresponded to that original input that I'm calling y gets multiplied by the same constant.
Okay.
Exponentials are the only functions that have that property, which is really, really important in physical applications. That's the reason that exponentials, for example, model radioactive decay, because there is a constant factor over constant periods of time.
Right.
All right, so much for talking. Let's now take a look at what we mean by that number e, the base of the exponential, the so-called natural exponential function. So e is defined as a limit, and it is this limit. You let x approach 0 so that the base here is approaching what? 1 plus 0, that is 1.
1.
The exponent, however, are reciprocals of very, very small numbers. So what kind of exponents do we have? If I take 1 over a really, really small number, the quotient is a really large number.
Right.
So this would look, if we were to substitute for the limits, would look like 0 to the power infinity, which is an indeterminate form.
Okay.
But one can, on the other hand, using a calculator, for example, or by hand, if you have the patience to compute, find approximations to this limit by taking x equal 1/10, 100th, and so on. And then you can get an approximation to the value in the limit, that is the number 2.71828, and it goes on forever. It's an irrational number. And that's the number that is called E, okay? Why would anybody in their right mind want to use that number as a basis for an exponential or a logarithm? Well, it is actually the number that makes the corresponding exponential f of x equal e to the x. We'll see it in a minute, but it makes this function be its own derivative, which is almost unimaginable, right? If I ask you what is the derivative of the sine, it's the cosine, it's a different function. If I ask you what's the derivative of x cubed, what is the derivative of x cubed?
3 to the...
3x squared, which is a different function. Mm-hmm. And that is typical. For any function, the derivative is a different function, except for this one. It is its own derivative. And of course, there are multiples. 7 times e to the x has 7 e to the x as its derivative. But now if we look at the function whose limit at 0 defines e, its graph is plotted here in brown. So we now see that the y-intercept, which is what would happen at 0, and the reason this is an empty point is that, of course, the algebraic expression is meaningless when x is 0, because you would have 1 over 0 in the exponent. Mm-hmm. But we see that it is indeed approaching a value, and it does seem to be a 2.7 something. And that's what E is. Okay?
Okay.
So again, if you take a calculator and you can find a good approximation with as many decimal digits as you want by taking smaller and smaller positive inputs, approaching 0. And so now we can leave a very good decimal approximation with more digits than we'll ever need or use, and then turn to the question of, okay, if we want to understand the behavior, the fact that e is bigger than 1 already tells us a lot about what the graph of the function will look like, because base bigger than 1, we know is the one that goes to infinity as x increases, has the intercept at 1, so that all holds. But let's focus about the rate of change, which means the derivative.
Okay.
And so if we take the natural exponential function, the graph will lie between that of 2 to the x and 3 to the x, because e is between 2 and 3. And then, as I said, the behavior is what we already know for all of them, with base bigger than 1, limit at infinity is infinite, and at minus infinity is 0, which means the x-axis is a horizontal asymptote. Domain minus infinity to infinity, and the range 0 to infinity. All right, rate of change, we said. So how do we find the value of f prime of x? Well, we will be using the definition of e that we just saw, that limit of 1 plus x to the exponent 1 over x. But how do we get there is answered by, let's start from the very beginning. What is the definition of f prime of x? Remember that difference quotient. The numerator is a change in x by a little number h, and then the denominator is the change in input. So the numerator is the difference of the values in f, so it's the change in f when you change the input by h. So what is it for this specific case? The function f of x is e to the x. What is f of x plus h then?
F of x.
We need to evaluate this exponential with input x plus h.
It would be f of e to the x plus h.
Not f of that. That is the value. F of any number is that number put as an exponent in e. So f of x plus h is x plus h exponent in e. F of x, of course, is written here. That's e to the x. And so now we can use properties for exponents that we just listed. What can you substitute algebraically for e to the power x plus h? A product of two numbers.
E to the x
times
e to the h.
Perfect. E to the x times e to the h. That's e to the x plus h. We copy minus e to the x. We copy division by h. And now we have two terms in the numerator. One is e to the x times e to the h. The other one is minus e to the x. Do you see a common factor in those two?
E to the x.
That's right. E to the x is a common factor. So we can pull it out. And then we have the fraction with the other two factors, e to the h in the first term, and then this e to the x is multiplied by 1 if we need another factor. That's where e to the h minus 1 comes from, right?
Right.
And now I would like to do something with this e to the x so that I can focus then on the limit of this ratio. Do you think it is allowed to bring this factor outside of the limit?
Yes.
That is very good. It is indeed allowed. Why is that? When we are saying, let's find this limit, what is the variable in the limit?
H is the variable.
H is the variable, which means that x is what?
X is a constant.
It's a constant. It's a fixed value, and therefore e to the x is a constant, and so the constant multiple rule allows us to bring the constant outside of the limit. And so now we can focus on what is the limit of e to the h minus 1 over h. And that goes back to the definition of limit, because not of limit, sorry, the limit definition of e, this formula here. So we can say that for small h, e is approximately equal to 1 plus h to the power 1 over h, right? That's the meaning of the limit.
Right.
That as h becomes really, really small, infinitesimally small, then you would have inequality here in the limit, but when you aren't at the limit, this is a good approximation.
Okay.
And so, since we really want not e but e to the h, let's raise both sides in this approximate equality to the power h. So we have e to the h is approximately equal to 1 plus h to the power 1 over h in the whole quantity to the power h. We raise both to the power h. On the left, we have the e to the h we want. On the right, we can use another property of exponents, power of a power.
Right.
What do we do with those two exponents?
You multiply them.
Excellent. And what is the product of h times 1 over h?
1.
1. And so an exponent of 1 means you may as well forget about it, which tells us that e to the h is approximately equal to 1 plus h, which is here in summary. And now we wanted e to the h minus 1, so we subtract 1 from from both sides. E to the h minus 1 is approximately h, but then we need to divide by h. So we divide both sides by h, and then we see that e to the h minus 1 over h, which is exactly what we wanted to approximate, is approximately 1.
Right.
And so what do you think would happen in the limit? The limit will be exactly equal. And so we now have f prime of x equal e to the x times what? What is this limit?
0. The limit is 1, sorry.
The limit is 1, e to the x times 1 is e to the x, and so we can now state that the derivative is the same function. Okay? And so a quick application of that is if we wanted, for example, to find the tangent line to the graph, as in this example, we are given the natural exponential function, and we want to find the line tangent to the graph at the point on the vertical axis. Remember that graphs of exponentials have all the same y-intercept. With a base bigger than 1, they are increasing, but they have always the same point on the vertical axis, which is what value is this?
X equals 0.
X is equal to 0, and y is equal to e to the 0.
Which is 1.
Which is 1, excellent. So the point P is the point 0, 1, as you correctly said. X is 0, y is 1. And so we can now use the function and the derivative that are the very same, and then recall that if we have a point x naught, in this case it's 0, then the equation of the tangent line is given by y minus f of x naught equals the slope, which is the value of the derivative at x naught, and then times x minus x naught. So there are 3 numbers we need to make this an equation that is complete. X naught we already said, that is what? 0. So this is just x. X minus 0 is x. And what do we know about f of x naught and f prime of x naught? Whatever that number is, it's going to be the same for both. And how do we find it? By letting in the exponential the exponent equal what?
0.
0. So e to the 0 is 1. You had already told me that. But then f prime of 0, the slope is also 1. And so we can now write the equation y minus 1 is equal to x. And if we plot the function, we had already seen it. Intercept at 1, that's the point we are looking at. In the tangent line, well, of course, you can rewrite y minus 1 equal x as y equal x plus 1. There we see that, well, the algebra we did matches, of course, the graphics, but the unique thing, recapping what we said about the equality that is framed here, the fact that the values in the derivatives are the same, what that tells us is that at any point on the graph of e to the x, the value is how high above the x-axis your point lies, and that number, whatever this number is, that's e to the x, is also the slope of the tangent line at that point.
Okay.
Okay? That's the meaning of the function matching its derivative. All right, so let's conclude by computing a couple of derivatives that have exponentials in them. So let's find the domain and the derivative in each of two cases. In the first one, even though we see a quotient, it's not an honest quotient because we can always, the numerator being constant, we've seen this in previous videos, suggests that it is probably a good idea to rewrite the algebraic expression with a negative exponent and no longer a quotient, right?
Right.
And so if we want to differentiate, this is the function f, we need to find its derivative. What properties of derivatives are we going to need? Well, the very first one will have to handle this exponent, so it's going to be the what rule? That is a power, so it's going to be the power rule.
Power rule.
All right. So what does that say? That if we want the derivative, first of all, there's a constant multiple, so we copy the constant multiple. And now what does the power rule tell us about 1 minus e to the x to the power minus 1?
You bring the negative 1 down.
The exponent becomes a factor. Excellent. And then?
And then 1 minus e to the x, and you add 1 to the exponent.
We subtract 1, so that becomes a minus 2. So the chain rule says that we still need to multiply the negative 2 power by what? The derivative of?
1 minus e to the x.
Exactly, which is the derivative of 1, which is 0, minus the derivative of e to the x, which is e to the x. Perfect. All right, so now let's simplify algebraically. 0 minus e to the x is minus e to the x. We can forget the 0. So we have minus e to the x times minus 1. That is e to the x times 3 is 3e to the x. And then I'm going to write a fraction bar because this expression with a negative exponent tells us that we have a denominator with exponent that is the opposite of that minus 2. So what is the denominator going to be here?
1 minus e to the x to the second power.
To the second power, perfect. And that is the derivative we were looking for. Then we are done. Now that's the second part. The first part asks what is the domain. So we need to look at the algebraic expression. And in principle, the domain are all real numbers except those that cause trouble. Trouble is typically division by 0 or trying to take square roots of negative numbers. So the domain will be all real numbers x, domain, all x and real numbers are usually represented by an r with a double bar, and this means is a member of. So x is a member of the reals, means x is a real number. But with what property? Well, what is it that we need is that the numerator here never causes any trouble, but the denominator should never be 0, right?
Right.
Which means that 1 minus e to the x, what restriction do I need to impose?
E cannot, or x cannot be 0.
1 minus e to the x cannot be 0 because we don't want to divide by 0. So if we now add we add e to the x to both sides, what is the conclusion? That 1 should not be equal to e to the x. And you were ahead of the game because that tells you what about x?
It should not be 0.
X cannot be 0. That's perfect. How do we know that? Because the only exponent that makes e to that exponent equal to 1 is the number 0. So that's the one we cannot have. The domain are all reals except 0. Very good. And let's conclude with the other exceptional case. Let's start here with the domain. What is it that we need? The number we take square root of, 1 minus 6 to the x. We need it non-negative because negative numbers don't have a real square root. So that is the same thing as saying that 1 has to be greater than or equal to 6 to the x. But I'm interested in x. So how can we solve for x if it appears in an exponent?
You can take the logarithm.
Excellent. We'll take logarithms on both sides. Should I take natural logarithms?
No.
No. Why not? The base here is what?
It's 6, so you should use base 6.
Exactly. So we want to take logarithms to base 6, and the inequality is preserved. The logarithm to base 6 of 1 should be bigger than the logarithm to base 6 of 6 to the x. But this very fancy, maybe threatening expression is what? The logarithm and the exponential are inverses, so it just gives you the exponent, right? So there's our restriction. X is less than or equal to, can we be more precise? What is the logarithm of 1?
1.
It is an exponent on 6 that gives you the value of 1. What exponent on 6 will give us 1?
0.
0. Excellent. So we have x less than or equal to 0. That's the domain. There's the x less than or equal to, and this is the number 0. And now what about the derivative? Well, we are going to use the chain rule just like before, except we start now with a square root. So the derivative is 1 over twice the square root of 1 minus 6 to the x. And then times, what does the chain rule say? The derivative of 1 minus 6 to the x, which is what? 1 has what derivative?
0.
0. And 6 to the x, we now discover we don't know it. We know the derivative of e to the x is e to the x. What about 6 to the x? Well, let's quickly take a look. We want d by dx of 6 to the x. What is 6 to the x? If we had base e, we would know what to do, so let's make it e. But the number 6 is not e, it's e to the natural log of 6. Because natural log and exponential with base e are inverses. And now we have that to the power x. So we can simplify that expression by bringing a power of a power as a product of the two exponents, right? So this is the derivative of e to the power x times ln 6. ln 6 is just some number. So by the chain rule, we know that this derivative of the exponential e to the some power that is not x is the same exponential times the derivative of the exponent, which is the exponent is a multiple of x. So what is the derivative of this exponent? The derivative of x is 1, so the derivative of a number times x is that number.
Right.
ln 6. And the first factor is just 6 to the x. So there we have the derivative here, minus 6 to the x ln 6. And now we can put it together as minus 6 to the x ln 6 divided by 2 times the root of 1 minus 6 to the x. This is f prime of x. Okay?
Okay.
Well, thank you.